Hello everyone and welcome back to another video. Today we'll be looking at another competitive programming question. This one will be taken from the British Informatics Olympiad and we'll be having a look at 2018 question 1. So let's have a look at the question. So the question is basically modeling some sort of debt repayment scenario, and I'll let you read the question, but I'll just explain the summary of the question. Pretty much, what's happening is that the debt of a person or something starts off at 100, and then, as with debt in real life, it accumulates interest over months, and obviously you need to pay off your debt like as every month goes by. And at the end of each month, you have to, depending on the interest rate, the value of the debt increases by a factor, and depending on the return rate, i.e. the value of the payback of the debt will decrease by a factor. Now, if we imagine the interest rate to be greater than the return rate, then the debt will never get paid off, right? Because then the value of the debt will increase faster than it goes down. So that won't be possible if you want to pay off the debt. That's pretty much the scenario we need to model. As the question states, we won't be given any invalid scenario. And there's one key part inside the question. Pretty much, the question says that when calculating percentages, the amount is rounded up to 2 decimal places. This is how it is in real life as well. And this basically adds some complications inside the code, and we'll be looking at how we deal with those when I show you the program. And now the input, we basically just accept two numbers, which are the interest rate and the return rate, and we have to output the final amount of money which is paid. Okay, and there's one key bit inside the question, and we'll see how. Okay, so initially inside the program, if I just quickly go to the code, we accept two inputs, the interest rate and the return rate. These are I and R. Now, the reason why I have labeled an interest rate and return rate is because I want to first convert them into decimals, since the 10 and 50 aren't very useful, but with these IR and RR, interest rate, return rate respectively, we can just directly multiply them, which is much more convenient than having to fiddle around with the percentages. And I also initialize these global variables, paid and debt. Paid representing the amount which has been paid, obviously, and debt again representing the amount of debt which is currently, like the person currently has. Now, so there's one complication inside this question, and we'll quickly go to the whiteboard to illustrate it. So pretty much, as I've stated, the question basically states that you need to round up debt to 2 decimal places. However, the thing which arises from situations like this is that if you have something like 15.446, then like a few more decimal places, let's say, we need to round this up to 15.45, which would be fine. And also let's say this were 15.42, we would also need to round this up to 15.45, which is fine. We can make a function for that. But then that's not the real complication of this question. The much bigger complication is the fact that computers don't store numbers exactly. So as I'm sure you know, the Intel system inside the computer stores everything as a string of 1 and 0s, right? Now, since this number in binary is something to the base 2, like it's made up of 2 to the base n, and then maybe like 4 to the base n, 8 to the base n, maybe like half to the base n as well, and then so on and so forth. But the point is, this is only made up of base 2 numbers, which means if we want to store something like 13.46, we can't actually store that in base 2 perfectly. Now, the way which computers mitigate this is they store a number like 13.46 as this, basically. Or like maybe 1 at the end. Point is, they make this negligibly different. Like, the difference between these two is basically 0. Like, it's going to be 1 times 10 to the minus 9, which is negligible. However, complication arises when we use any sort of rounding things inside our functions. This number wouldn't be treated as 13.46, it would be treated as 13.46000001. Hence, this would basically be rounded up to 13.47. And you can see why something like this would actually be a serious issue, because ultimately we will be storing numbers like this. If we round them up, they'll become 13.47, which means we've effectively just induced 1 extra p of debt, which in real life is obviously ridiculous, since you wouldn't want just money to be like getting invented from nowhere, or money being taken away from you for no reason. And for the case of our program, it would basically cause an incorrect answer. So the way in which we mitigate this error is that we must keep things to 20 decimal places, a very, very high accuracy. Only then will this error be mitigated. I'll explain how shortly. So if we just go back to the whiteboard, pretty much, if we keep everything to 20 decimal places, you might be thinking that, well, we still have the same issue of when we round it up, we'll still be inducing some sort of error, right? But then, basically, the way which we can mitigate this is that we need to make our own round up function, or we can't just use some sort of ceil function or something within Python. And the way this will work is that we'll round it normally first. So 13.46 blah 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 rounds to this normally. And now what we'll do is that we'll check whether the number which it's been rounded to normally, this isn't the round up, whether this is larger or less than the original number. So now in this case it will be less than, since the original number has some additional 1 thing. However, we'll be checking whether it's less than to a certain dp. So like, let's say to like 5 dp, if this one's less than this one, then we basically know that we need to round this up, we can't round it down. However, if to 5 dp they're basically the same, then we can just stick with this, okay? And now, let's look at another example. Let's say we have 13.46235, whatever. Now, this basically rounds to 13.46. This number is less than 13.463235, whatever. This basically means that instead of rounding it to 13.46, we need to add 0.01 to it, thus making it 13.47, which is the rounded up version of this. That's pretty much how we're going to go around this problem of rounding inside our code. Now let's just have a quick look at the program. So, and now we basically have this round up function. This basically says what I was explaining on the whiteboard. We round it up to 2 decimal places. If the number is greater than none, then we basically add 0.01, sorry. So exactly I was saying that if the number is greater, then we add 1. However, you might be thinking that, what are the error of like 0.460001? Now that error will basically be mitigated since we're rounding it here to 2 dp anyway, right, as I explained on the whiteboard. Thus we won't have that error, and we also won't lose accuracy since this number will then be rounded to 2 dp, and everywhere else in the program we're keeping it to 20 dp. Okay? So now let's have a look at the other functions. So interest, we're basically just multiplying the final interest, final amount of money, times by the original, by the interest rate basically. And then we round the interest rate to 20 decimal places. And then we return the rounded out version of this final interest rate. And now this is the repayment function, which is the main block of the code inside here. So we basically have this global variable paid. As explained earlier, this is initialized to the value of how much debt has been paid off so far. And this is the amount to be repaid. This amount to be repaid is local, and it's storing the value of the amount to be repaid in this particular session, if you like, or in this particular month. And this will basically be the amount. It will initially take the rounded up version of the original interest rate multiplied by the return rate, okay? Since that's the amount which gets repaid, and the return rate will be some sort of decimal, like as over here, it will be like maybe 0.3, let's say pay 30% each month. And now we'll round this to 20 decimal places as well. And then the final amount to be repaid will be the max of the amount to be repaid here, which is rounded to 20 decimal places, and 50. Now the reason why we have 50 is if we just go to the question, it basically states that if the amount repaid is less than 50, then you have to repay 50. If we just go here, it basically says it over here. The repayment is a fixed percentage of the debt, or 50, whichever one is larger. And we're doing exactly that. We're just taking whichever one is larger out of the two, the amount to be repaid and 50. And that becomes the final amount to be repaid. Okay? Now, if the final amount to be repaid is less than the original amount, the original being here, then we basically just add the amount to be repaid to paid. The original is basically the current outstanding debt, if you like. And the reason why we're doing this is because if we just blindly subtracted the amount to be repaid like this, that could result in a negative answer, right? Since let's say the original debt to be repaid is 30 units, but the amount calculated is 50. So then we'll basically be paying them 50, and the amount which we paid will be 20 greater than what it should be, since we've paid them so much that they somehow owe us money, like we owe them negative money, which means they owe us money. That doesn't make any sense. So then we're only going to be doing this if the final amount to be repaid is less than the original. If it's greater than the original, then we only pay how much is outstanding, and then we return 0. This is because the amount of outstanding debt now is 0, since we've paid back everything. And this basically just simulates the process of adding debt each month. So the debt increases by the interest rate, the debt decreases by the repayment, and don't forget the global variable paid will be getting updated inside this if loop anyway. So once we've done this until the debt is equal to 0, then we'll bring out of this while loop and we'll basically print the rounded debt. The reason why we're rounding this is if we didn't round this, it would give it to like 8 dp or whatever, which isn't what the question asks for. It only asks it to 2 dp, and that's basically it. So now if we just go to the mark scheme and test it on a few sample inputs. So let's go here. Maybe let's just test it on this one. It basically gives us 143.46, which if we go back to the question is the correct answer. And now let's just test it on maybe this one as well. And now let's go back to the program. It gives us 6755.51, which is also correct. So as you can see, this code basically works. And that's basically it for today's video. I hope you enjoyed something, and hopefully you learned something new about tackling this question. Maybe the idea of splitting each part into 3 functions, maybe the idea of rounding up into ADP, maybe the binary thing. And I really hope you enjoyed this video, and I hope to see you in another video next time. Thank you very much for watching.